and in OBS, and so we'll see what exactly happens there. Okay, so let's get the rules of engagement clear on that. So it's an in-person examination. That's the first rule of engagement. The what's the second rule of engagement? It's an examination in Canvas. So you need to be having have Canvas. So you're gonna need a laptop, or I suggest a laptop. Third rule of engagement. Certainly, the only things that are available to you are the content of the Canvas course. So that means specifically, that doesn't mean everything in the Canvas course. It doesn't mean you can open up videos, you can open up anything. It means very specifically what's available in the lecture slides and the MATLAB materials, PDFs, the things that are directly available in these links, all the way up to lecture and including lecture 8, which is today's lecture. So that's what's available.
Excuse me, Dr. Willis.
Yeah.
I'm sorry, before you move on, could you allow access to lecture 8 slides?
Yeah, well, yes, very much so. Yeah, let's go ahead and see what's going on there. Yeah, lecture 8 should be available to you. Well, the midterm solutions, I'm unfortunately not going to make available, but how this could...
Yes, sorry, maybe it's my apologies.
Yeah, it seems like it should be available to you. If I make an errant click here, make sure you go out and run over there. Anyways, it should be. Does anyone else have trouble accessing that? I certainly want you to have that.
Yeah, I'm not able to see them either.
Yeah, it's 8A I'm able to access, but not just lecture 8, which is a little bit larger.
Yeah, I can't either.
It's a 2.3 megabytes. The other one's only 390 kilobytes.
What's going on? Well, what's going on? So, okay, this is...
Dr. Willis, it's because the module itself needs to be published.
Oh, yes, you're exactly right. Thank you, person from the ether that I don't know said that. Yes. So, yes. Thank you, whoever said that. So all of this should now be available. And so all these lectures, all of this stuff. Apologies for not having made that already available. Of course, I guess the file was available, but this thing wasn't visible, right? So sorry about that. And so we'll have this one next week, and then you should have, well, let's see, I'll make lecture 9 also available, but it's not going to really, we'll that way if you want to get ahead of things, maybe after the midterm, you can certainly look at that. Any other, so I want that to be abundantly clear, what's available. When you do come to the lecture, more on the rules of engagement, so there's the assignment itself. So we have the review for the midterm exam is available to you. The midterm exam itself is here. 75 minutes, not multiple attempts, in-person online exam. You must be there. We'll take attendance. If you're not in attendance, you will be assigned a grade of 0. For those of you that might take the test at the Disability Services, you certainly need to let me know. You must submit your exam before leaving the classroom. I'll be monitoring the submissions, and so if you want to submit and leave early, just give me a nod that as you walk out, so I can make sure that you're submitted. Expectations is, of course, your work is your own. You can use MATLAB, you can use the slides, and that's what you have available to you. That's quite a lot of material to support you. And be prepared at the end of the exam to upload a PDF where you capture your work and attach it to you as the last problem to the exam, which we've practiced several times at this point. And just to try and make that as error-free as possible, you're responsible for doing that as part of your exam work. You can't leave the exam and then submit that afterwards. It will not be accepted.
Dr. Willis.
Yeah.
Oh, for that part, we can take our cell phones to scan it.
Yeah, you bet. I
Okay.
fully expect you guys to take your cell phones in and scan it. I don't want you working on your cell phones or communicating with other folks. You know, there's no communication either by word of mouth or via electronic means while you're on the exam. I'll have everyone be facing the back wall instead of facing me. That will make all screens visible to me so that I can make sure that folks are following the directions of the exam. And and if you do need to use the restroom, the only thing I ask is that you leave your cell phone either, you know, if you happen to be on your way, you can leave it up where I'm at sitting, or you can leave it at your desk, but just not to bring it into the restroom is what I request. And so, are there any questions about the rules of engagement for the exam? Okay, good. So having established that, let's see. I wanted to also say that the assignment is out there where you can do a practice for the review homework for the midterm. That's available, and we're going to have this last lecture, which sort of, you know, for the folks that have been following closely how all this stuff we've been talking about the last, well, really 4 lectures, because we do this like these 3 different topics about 3 different realizations of linear time invariant systems. So it's like a 3-lecture series. The 4th lecture ties it all up. So if there are no questions, I'm going to jump into that lecture, and hopefully, and a lecture actually ends up also being sort of a review, kind of showing you all these techniques for solution that we've come across as we've gone through the class up to this point. So before jumping in, is there any other questions? I do want to point out that we're posting these. I've mentioned this a couple of times, but I want to keep mentioning it. But you know, work solutions are out there. The spring 2022 work solutions. We're constantly adding to it, and you know, there's quite a body of solutions out there. So the latest being homework 4, question 9, homework 4, question 8, question 6, question 3, so forth and so on. So there's lots and lots of work solutions to use as part of your study materials, where we go through all of the details, everything, and to try and you know, make it clear how to practice these techniques for solution. So I'm not hearing any questions. And
before we start,
yeah?
Dr. Rose, I just wanted to say it looks kind of blurry for me. I'm not sure. I just want you to keep in mind while you do your analysis.
Yeah, when I scroll through things, it will get blurry. But hopefully, when I hold the slide constant for a while, that'll clarify. So we'll So I had a question in chat: were you allowed to use our personal notes and quizzes? So I want to say very clearly and emphatically, no. I've described exactly what you can use, and anything that falls outside of the range of what I've described you can use, you cannot. So I'm a linear, sort of. I guess I'm a time invariant system in that regard. You can ask me this question at any moment in time, future, past, or present, and I'll always say the same thing. No, you can only use exactly what I've specified. Do not bring in any other materials. If you bring in other materials and use them during the exam, that constitutes cheating. To be clear, I want to be absolutely clear about that. And so, that would be an academic integrity violation that we would have to discuss. So, let's see. Any other... So we have the blurry comment. Let's just see where that goes. Hopefully that'll mitigate itself when I go to the slide. You know, when I scroll through things quickly, that'll definitely be an issue, but hopefully it'll mitigate when I go to the slides. And let me know if it doesn't. All right, then I'll go ahead and start the lecture. Okay, so this is lecture 8. This is a lecture sort of to end all lectures as it comes to linear time invariant modeling. All right, so there's three different ways that we describe linear time invariant systems as these things present in chapter 2. And this is really a lecture to summarize all of that. And so it's all of chapter 2, and we're kind of thinking about the midterm exam. Okay, and so we're going to talk about all the concepts of chapter 2 and how these concepts interact. And specifically, we're really focusing on these three different representations of a linear time invariant system. So this is sort of the triangle of knowledge as it pertains to DSP. Okay, we have three different representations of a linear and time invariant system. So we talked about these three different representations in lectures 5, 6, and 7. Lecture 5 was all about the impulse response, H of n. This is the lecture all about H of n. That's where we talked about convolution and things like that. Lecture 6 was all about difference equations, how you solve them, how they represent linear time, and when they're linear time invariant, when they're not, how to solve them, and how they relate to other things. So this is some equation where you have y of n minus k, some kind of versions, sum of those is equal to some collection of x of n minus k for, well, delayed versions of y are equal to delayed versions of x. This is sort of the general form of a difference equation. So in impulse response, you have an h, and then you talk about convolution, which is the sum of the input, x of k times x, or times h of n minus k. And that's how you represent the output, y of n. And then over here we have, this is lecture 7, the frequency response. And this is the DTFT. And so here we're representing the impulse response as h e to the j omega. And we think of the big thing here is that if you do convolution in the time domain or the sample domain, that's multiplication in the frequency domain. So, one of the major things to look at is this y e to the j omega is equal to h e to the j omega times x e to the j omega. And so using these three different concepts, we can get from any one part of this triangle to any other. For example, if you have an impulse response h of n and you want to get a difference equation, you can use the convolution equation and substitute in values of h. This sums, and then if those values will turn into constants, and then you end up getting an equation in x and y. And we've done that before. Like for example, h of n is equal to delta of n minus 1. And then how do you represent, if we want to get y over n in terms of x of n using that? We do convolution. So we do x of n convolved with h of n. And what is x of n convolved with h of n?
X of n. Oh,
minus
k.
Right, because it's got this delta of n minus 1. By the sifting property, it's x of n minus 1. And now we've converted our representation of a system from h of n, which is an impulse response, to a difference equation. Y of n is equal to x of n minus 1. So convolution lets us go. So we're just going to discuss all these different directions. As you can see, there are three representations, and every representation is related to every other representation with these arrows. These arrows use different sort of relations to go in one direction than the other. For example, if you have h of n, you want h e to the j omega, you use the DTFT. You have h e to the j omega, and you want h of n, you use the inverse discrete time Fourier transform. And so you can do the same thing for difference equations. You take the DTFT of a difference equation, take the iDTFT of a difference equation. So we're going to look at all of that stuff. Okay, so here we're going to look at this particular edge between all of the different representations. And if you have an impulse response, h of n, there are two different kinds of impulse responses. What are the two different kinds? FIR, IIR. An impulse response can either be finite in length, meaning a finite impulse response, or infinite in length, infinite impulse response. If we want a difference equation and we have a finite length impulse response, we just substitute the values of h in as constants. We get an equation where h ends up being the coefficients of the delayed versions of x, and we substitute the values in. Here, there's 1 when n is equal to -1. Well, let's see. When n is equal to negative, h of -1 goes here, so that 1 goes in here. H of 0, that has the value 3, that goes in here. And h of 1, that has the value 1. That's x of n minus 1. So h of 1, I think there's a sign error here. Right? H of... Oh, it's -1. Oh, I see. The value is -1. So the -1 goes in here, and that's why we have a minus there. So that's hopefully that's clear. That's just using the convolution equation to go from one to the other. Any questions on that? Okay, so here for the IIR, let me kind of, I know that I need to have zoom up, so don't have my chat window available, so it's hard to know if people are in fact asking questions. Just bear with me while I get that.
Dr. Wells, I had a question if you have a moment. On your last slide, what was the meaning of 5, 6, and 7? You just wrote down number 5, the number 6, number 7.
Yeah, that was lecture number 5. Is about,
okay.
Yeah. No, you're good. You're good. That's fine. That's a good question. So lecture number 5 is about the sample domain representation. Lecture 6 was about the difference equation representation, and lecture 7. Now we're in lecture 8 right now. Lecture 7 was about the DTFT and iDTFT representation. So yeah, this is the way to do that. Okay. So let's see. You know what? All right. So let's see. Andy asked a question in chat whether or not to bring a TI-84 calculator. You know what? People can use MATLAB. I would strongly suggest using MATLAB. You know what? You can. I'm gonna rescind the no. If folks can use MATLAB, you certainly can use a TI-84 calculator. Absolutely, as long as it doesn't pull up, PDFs or have programs in it. Now, if you pull up a TI-84 calculator that's basically running your own little scripts to do things, well, that we're going to have a significant problem with. So I guess, that TI-84 calculator is always not going to be as good as MATLAB, I'll tell you that. But you certainly can use it. So I'm going to rescind my no and say yes. Sorry, Andy. I hope that is a more clear answer. But I think the best calculator you can get is really MATLAB. That's kind of my suggestion. And if you review some of the MATLAB code, you can really make yourself. It can give you a competitive edge to make sure you have maybe more time to analyze your solutions. And so what does that mean? That means if you want to bring in any calculator, that is fine, even if that calculator is in fact your phone. But remember, it's for calculation, not for communication. All right, so let's see. What are we doing here? Well, we're going the other way. So in the last slide, we went from impulse response to difference equation. We went this way. We're going to go from difference equation back to impulse response. So this is a difference equation. X is on the left and Y is on the right. No problem. It doesn't matter. An equation is a tautology. I mean, you can flip the sides. It doesn't matter. We typically see Y on the right, but that's just no matter. So we take the DTFT. And so x of n is delayed by 1. It gives you this term here. X, it's for a transform. We write as x e to the j omega. And then we have by linearity, anytime you multiply it, it just goes into the Fourier domain as a scalar multiple. And then you do the same for y. And so there are 2 terms in y. We're going to just factor out the y ahead of time and get a 1 minus 2.5 e to the minus j omega. And that gives you the terms in y. And that comes by, this is the term by term thing, and we've actually factored it out here. And of course now we have x and y, and so I can multiply. I can take this term to this side, and I can take this term to this side and divide, and I can get y over x is equal to 1 over, so 4/5 e to the minus j omega, this term here, divided by this term here. And that, in fact, is the ratio of y to x, so that is, in fact, the discrete time Fourier transform of the impulse response of this system. Well, if I can take this equation right here back into the sample domain, I can then get h of n. So in fact, what we're actually doing here is so I drew this arrow, and I'm gonna subsequently delete it. So I drew this arrow like that, and we're not actually following that, are we? We're actually taking the difference equation. We're taking the DTFT. We're going here, and then we're taking the iDTFT. We're going that way. Does everyone see that? We're kind of not charting this course the way that I originally drew it. And it just shows you the truth of this triangle here, like how you can move around. So in fact, let's see, what we're doing here is we're going to say, hey, let's get this and take the DTFT. We get this representation, and then we're going to try and find how to inverse transform this. Well, this ends up being a delay of 1 by the delay property. We know how to inverse transform this already. Does anyone remember what the inverse transform of that should be? The key here is that this is an alpha, right? This is an alpha to the n u of n.
So it's negative 2 over 5.
Oh, it's not negative. Be careful. 1
positive, sorry.
1 over 1 minus a alpha e to the minus j omega for magnitude of alpha less than 1 under the Fourier transformation goes to what?
Magnitude.
Alpha to the n u of n, right? So this negative sign doesn't go with the alpha. Like this is a positive over here, right? And this one's a negative. So since there's a minus 2 over 5 here, this is a plus 2 to the 5. Now this n minus 1 comes from the e to the minus j omega. That's by the delay property, and it also delays u of n. So, and then this 4/5 is just a constant out in front, and it goes here. Does everyone follow how that transformation occurred? Okay.
Yeah, Dr. Willis, I have a quick question. So what about if we were to have 1 plus alpha e to the minus j omega in the denominator?
1 plus alpha e to the minus j omega. Yeah, you actually have that in the homework, right? So in fact, we talked about that over email. So this is a great, that's a great question. So let's.
N plus 1 and unit step n plus 1.
Well, you have to be a little tricksy here, or there involves just a little manipulation, right? You have to realize that you can write this as minus alpha.
Negative.
You can write it that way, and it's still, you haven't changed the equation, right?
Right.
And so, can you inverse transform that?
Yes.
Yes, sir.
Right. So it ends up being minus alpha to the n u of n, right?
Right.
And so if you look at so me and Eric actually discussed this specifically, and it's worked out as homework for question 9 or something
Question
like
9,
that.
I believe.
Yeah. And this happens twice, right? There's twice it happens, and you can see how that works. But we kind of just, when there's a plus there, you sort of rewrite it as minus the negative, and that way, and then the negative ends up. That's how you get a negative in there. So anytime you see a plus.
Dr. Willis, in regard to that though, the shift, if it was e to the negative j omega, that shift would have to be accounted for, right? So it would be plus 1, or is it because there's no e to the negative? So when that's how it goes, negative alpha to the end u of n.
Yeah, this is what it is.
Yeah, the indicator, if in case, it would be n plus 1 or n minus 1.
No.
No, so yeah, this n or n would be plus 1 or minus 1 if there was an e to the j omega. So if there was an e to the j omega here, that would shift it in time.
Perfect. Okay.
Yeah.
Perfect.
Yeah. If there was an e to the minus j omega, that would put a minus 1 here, and that's using the Fourier transform shift property That means that if you Fourier transform x of n minus n naught, under the Fourier transform, you get e to the minus j omega n naught x e to the j omega. And so think of this like, so if you have u of, so say 1/2 to minus 1/2 to the, let's do something, minus 1/2 to the n, u minus 1, u of n minus 1. Okay, so we already know that what that would be under the Fourier transformation without the delay, it would be 1 over 1 plus, and I'll write it in like this so that we kind of know that what about that minus trick, e to the minus j omega. And then to get the n minus 1 shift in both in the exponents and in the step function position, we would multiply it by e to the minus j omega. All make sense? Hopefully.
Yes, thank you.
All right, great. So any other questions before I move to the next slide? So again, having this triangle in your mind and knowing how to go from one place to the other, chart your course, right? If I'm here and I want to get there, I can go, all of these edges. You can use whatever edges of that triangle you have available. If something fails, try another direction. There's always two ways to get to, there's two ways to get to every node. Okay, difference equation to impulse response. Difference equation to impulse response. Difference equation, so we're going in a different direction. I think we're going to go this way this time. Okay, this one's the actual, where we actually solve things out. And this is, you actually have to take this path if you have non-zero initial conditions. In this particular case, the initial conditions here are both 0. You could take the DTFT path if you were very careful, because it's linear and time invariant. If you have non-zero initial conditions, you really have to just solve it out like it's done on this slide, this technique for solution. So here we have a difference equation. It's a second order difference equation because the delay is 2. The input is the delta function. Oh, that means that we're actually calculating a homogeneous solution. And so we calculate the homogeneous solution here. And we get the factors of the characteristic polynomial and the roots. And those roots end up being our the alpha to the n's. And then we have these unknown alpha coefficients, alpha 1 and alpha 2, that we'll solve for once we have a particular solution that's meaningful, right? In this particular case, the particular solution for a homogeneous solution is just 0, so there's nothing to do. So if we add that to the homogeneous solution, they just have the homogeneous solution. And this is the general solution of this equation. And then the system is at rest because we're solving for the impulse response, and we can use any initial conditions we like. In this case, we'll use y of minus 1 and y of minus 2 is equal to 0, but we could use y of negative anything is equal to 0 because the system is at rest means that. Okay, so then we solve this. Y of 0 is equal to, we plug this is using the actual difference equation. So y of 0 is equal to delta of 0, which is the input, minus y of minus 1, which is this term, moved to the other side, minus 6 y of minus 2, that's this term, and then we get this equation in alpha 1 and alpha 2. Y of 1, now we have to look at the output at and after the time that the input is applied. So the input is applied at 0. So we look at y of 0 and y of 1 for our two initial conditions. We calculate those initial conditions, and we get equation 1 in alpha and 1 in alpha 2, and equation 2 in alpha 1 and alpha 2. And once we have these two equations, we solve them simultaneously, and we get values for alpha 1 and alpha 2, and then we substitute those into the general solution, and we have the solution for all n. That is our technique for solution there. Any questions on that?
Yes, Dr. Willis. Can you explain why the particular solution was 0?
Yeah, so the particular solution is the same form of the input, and so the input takes on a non-zero value only at 0. So for all time after time 0, it actually The input is 0, right? And so the output, so you could write something like yp of n is equal to beta times 0. Like if you were taking it as just like, like what we always do, it's beta times the same thing, but the form of the input is 0. So beta times 0 is 0, so that means that we don't even, the particular solution for this particular example is just 0.
Okay, it's definitely a little weird, but I can go with it for now.
Yeah, well, and also think of it this way. Like, when the input is the impulse like this, that is the definition of the impulse response. Right? And so this here is the impulse response. So, so it's kind of like, since we've already captured the behavior of the impulse response, it's kind of like there's nothing further to capture in terms of the behavior of the system. Might be another way of explaining it. It can be, it's, I don't know of any other way to explain why the particular solution is 0 other than the fact that the input is always 0 except at 0. And so, other circumstances we've had inputs like, 8u of n, right? This exists for all time, so it's sort of the value 8 for any time n greater than 0. So then we get a solution that kind of looks like that respects the value 8 being put into the system, at all times n. So the analog here is like, this is just 0 times u of n, and so it's like always. So I see a question in chat from Daryl. The solution is valid for n greater than or equal to 0. Yes. But we also know the state of the system before 0 is at rest. So we actually know the state of everything for all time. So, but yeah, the only time you'll see non-zero value will be at 0 and later. So I think that maybe we're both right. Like it seems like we know all of the values for all time, but they're only non-zero values at and after 0, if that helps. Did I answer all of the questions? Okay. All right. Well, then we'll move on.
Sorry, Dr. Wills.
Yeah.
Does that mean if you calculate better, it would be 0? Even if you do the whole math thing and then calculate better, it would be 0?
Yeah. In this particular case, if you really wanted to calculate out the particular solution, you'd take beta times 0. You'd substitute beta times 0 in here, here, and here, and you get 0, 0, 0, and you'd find that 0 is equal to 0, and then it's just nowhere to go. It's like everything is nullified.
Yes.
Right. Yeah. So you can do that. And I sort of short-circuited that process. So the process, you can go through the process. I just kind of short-circuited it. But you will still get the same result if you go through the process.
Thank you.
Yeah, thank you.
One more thing, Dr. Wallace.
Yeah.
On the line right under delta n, you put a xn equal to 0. Is that a part of the question, or?
Delta n, xn is.
Right under xn equals to delta n, there is an xn says xn equals to 0.
Yes.
What about that? Yeah. Is that part of the question?
No, that's when you compute the homogeneous solution.
Okay.
Yeah, you always assign the input to 0. Okay, and that's the same thing that you do in differential equations. Like when you calculate the homogeneous solution, you just set the input to 0.
Okay, I see that.
Yeah. Okay. Nice. All excellent questions. Thank you for your questions there. If there are no more, I'm going to go on, but feel free to ask some if something comes up. Okay. Difference equation to impulse response. Okay, so we're here, and we're going to go here again. Now, we did so in this particular case, we went difference equation to impulse response for an IIR difference equation, right? Something that has feedback with y's. So this is in the case when we have an FIR, all right? And it's really simple. If you have an FIR filter, meaning no delays in y, there's only one term in y, all you do is you substitute deltas for the x's, and you are done. This x goes to a delta, you are done. It's just that easy. So, So that should be an easy one if it's FIR. Everyone clear on that? Because again, when you're calculating the impulse response, what are you doing? You're letting x of n equal delta of n. That is what the impulse response is. And therefore, if x of n is delta of n, x of n minus 2 is delta of n minus 2. X of n minus 1 is delta of n. It's almost tricky because it's so straightforward if you use the definition. But well, I'm just not going to discuss it more because it might even get more tricky if I overcomplicate it by discussing it more. So I'm going to move on. Okay, so we just talked all about this edge of the triangle, this left or this right edge. Let's talk about the left edge. The left edge moves between the impulse response and the frequency response, so the frequency representation of an impulse response. So when we're going in this direction, we start with an h of n and we're going to an h e to the j omega. Okay, we can do this. So we just take the Fourier transform. So if h of n is this is a FIR system. So if it's an FIR, we just take the Fourier transform of what we see. So this is delta of n minus 2. What's the Fourier transform if you have delta of n? What is the Fourier transform of that?
It'll be e to the j omega.
Well, just delta of n. What's the Fourier transform?
Just one. Oh, one.
Just
one.
one. Second y of n o sine b h of n since the impulse response. There's a question by Seth. Slide 7. Yes, y of n, and this is also equal to y of n is also equal to h of n. Yes, so this y of n is h of n if x of n is equal to delta of n. Yes, that is very correct. So yes, the Fourier transform of the delta function is 1, and the Fourier transform of a function, any function, if we delay it, x of n minus n naught, when delayed, is x e to the minus j omega n naught x e to the j omega. So using these two properties, we know the Fourier, this x is at delta, and we have a delay of 2, so we have 1 e to the minus j omega 2. That's so, and then we have a constant out in front, and so the constant goes straight into the Fourier domain by linearity, or the scaling property more accurately. Linearity uses both addition and the scaling property, so we are using it when we start considering adding these terms. So everyone understands how we got this term right here, right? And remember, there was a partial fractions problem where we did something like a over e to the minus j omega, and we did a. So remember that's equal to e to the j omega. That is a delta function in terms of a Fourier transform. So let's see. I'm just gonna get rid of that because that's sort of an aside comment. Okay, so then we Fourier transform the next term. Well, delta of n minus 1, there's a 1 here, so that's 1 e to the minus j omega, minus 1 delta of n plus 2, that's minus 1 e to the 2j omega, and we have successfully Fourier transformed this function from the sample domain to the DTFT, the discrete time Fourier transform domain. And it's FIR. So it's FIR, it's just stuff like this. If it's IIR, it's we have to use we might use our equations, we might use a table, we might do factor. In this particular case, we can solve this sort of 3 different ways. We can use the table, we can factorize, or we can actually do the DTFT evaluation. So if we do the evaluation of the DTFT, we do it. This is what happens. We just plug in the function to the DTFT. We find that only terms that have n greater than or equal to 1 matter. So we simplify the bounds. And after we simplify the bounds, then we got a sum that goes from 1 to infinity. Well, we can make it start at 0 by factoring out a term. We did this before. Or we could change the summation by change the variables. But anyways, we get it to a sum that starts at 0. And then we apply the formula, that one formula that drives the existence of DSP, the sum from n equals 0 to infinity alpha to the n is equal to 1 over 1 minus alpha as long as the magnitude of alpha is less than 1, and that drives all of these. That's how we get from here to there, and since we've taken this factor out, it goes to here. And so that's I want to do this. I'm going to actually calculate the DTFT and do it analytically. Method 2, I'm going to take a trick out of the Willis page, and I'm going to say, hey, I'm going to try and get the exponent of n and the delay of u to the n to be the same. How am I going to do that? I'm going to factor out a 1/2, and when I factor out a 1/2 from 1/2 to the n, it becomes 1/2 to the n minus 1. Well, then I have 1/2, and then I know directly how to Fourier transform this. We're going to use this property, this delay property, and then we're going to use that I know the Fourier transform of alpha to the n u of n. And we can write it as 1 over 1 minus 1/2 e to the minus j omega, put in the term for the delay, and then we have to also incorporate the 1/2, so that gives you this factor, and now we have, just by inspection and using some properties, we write down the solution directly, and we haven't used a lick of math here. We've just used a way to do some factorizations and get things in the same format as that which we have in our table. Any questions about this?
Dr. West, I don't have a question about this, but I was just thinking about it. I know we don't have time to review everything, but I see you didn't put in like stability, causality, and something like that, samples per second kind of stuff we started with.
Signal metrics. There is absolutely.
Okay.
Yeah, I mean, I don't know if you've seen all of this lecture, but probably not, because it was just open to you. But
I see.
It's you've got. It's a beast.
Okay, awesome.
It's a beast of content here. There's a lot here. 39 slides. We are definitely not going to get through them all, right? We've only got 30 minutes. But these slides are, it's part of your study materials too. In fact, this is sort of a slideshow to end all slideshows in terms of what you need on the midterm. And it kind of has all of the techniques for solution, and it does talk about stability. Like here's the system properties, right? So it has a lot of the important properties. We're sort of working, I think, in my opinion, the most important aspects of this point in time is knowing all of the representations for linear time invariant systems and disentangling all of these different representations, which is why I spend time discussing this triangle and all of these ways to go from one place to another, because I find that often we don't take the time to sit and understand the bigger picture. And so this is a bigger picture part, and then we'll kind of go into the other stuff is sort of a little bit harder to link all together, but it's there. So I'm not sure if I answered that question or avoided it, but I just want to say that So we can try and get to it, but I want to get through this stuff, and then we maybe at if I get through this stuff, maybe we can stop at 2:05 and have 10 minutes of like the students drive the lecture, tell me where to go and what to talk about. Let's try and do that. Okay, so to do that, let's get through the rest of this. All right, so Fourier transform to impulse response. Okay, so we start off here and we want to go there. Okay, so I start off with an impulse response, h e to the j omega, and I want to go, this is for an FIR, impulse response. FIR impulse responses are all going to look like this. They're just going to be powers of e to the j omega, right? Because it's FIR, it's the sum of delta functions. These are all delta function transforms. So when you inverse transform it, you're going to get coefficients multiplied by delayed delta functions. And so, not surprisingly, it's kind of exactly the inverse of what we did for the forward transform of an FIR filter, which, I don't know, I do it for completeness, but I guess it might be a little bit boring on your side. But at least that way you know that there's duality there. Okay, IIR. Well, IIR isn't quite as simple. You often end up with a ratio of polynomials in e to the minus j omega. Like, I want you to kind of think of this as like 5 minus s over minus s squared plus 1/4 s plus 1. I mean, you do this stuff all the time in differential equations. e to the minus j omega acts a lot like just a variable x or s or what have you. So you don't let it trip you up. Don't let it trip you up. It is not the Laplace domain. It is not we are in a different domain, but its behavior from an algebraic perspective is the same. And so a lot of students stumble, trying to manipulate it. And, you kind of move it together and keep all of their signs the same, and it just behaves like an X. So don't know why I say that. It's probably obvious to all of you, but it's just a recommendation.
So is this even true, even though they have different values of j omega, like -2 j omega and -j omega?
Yeah, I was about to add that. That might be a typo.
No, it's true. So I'm gonna write this as e to the minus j omega squared. So I look at this and I see -1/8 s squared minus 1
Yeah, that makes sense.
1/4 s plus 1 over 5 minus s. That's how I see this, and you have to factor that.
Oh, I see. Because you added the exponent, so therefore you got.
Yeah. That you kind of that's and students can get tripped up and not see this as a factorizable thing, but it's certainly factorizable, right? This is a quadratic in S, right? Or this is a quadratic in e to the minus j omega. Doesn't look like it, maybe. I don't know. It does to me, but that's because I think of it like this. And so, yeah, it's super important, right? It's super important to know how to factor stuff, because you have to know the collect terms in e to the minus j omega. Before, you would just collect terms in S, and there's no lack. It's completely clear, right? There's no possible ambiguity. Here there is possible ambiguity, and I'm trying to disambiguate, like how to proceed algebraically. Anyways, I'm sure that's all super clear. But it's always good to just discuss it to try and prevent confusion. So, anyways, this is what we get. We get a ratio of polynomials in e to the minus j omega. I think of this as a polynomial in e to the minus j omega, right? This is e to the minus j omega squared. This is this is that to the first power. This is to the first power. That's why I kind of do this silly substitution over here. And I'm kind of thinking of s is equal to e to the minus j omega, just for the sake of being comfortable with it. So what do? Well, we factor things. So if we were to factor this polynomial, we get factors of -1/2 and plus 1/4. And so there is a difference here, in terms of how the factors look. But this is how you factor such a polynomial. And then you do partial fractions, and so in partial fractions you represent the partial fractions as unknown quantities over each side, and then you just solve. You solve for a and b, and so you solve for a and b by equating coefficients, and there's a very detailed versions of that in the homework a number of times, in the slides a number of times, and it's sort of just given here. Like, it's not, I haven't worked out all the details for lack of space, really, but you work these out. Then you have the partial fraction expansion, so this ratio here is equivalent to this on the right, and then you inverse transform each term and use linearity to say that the inverse transform of the terms of the sum of the terms is equal to the sum of the inverse transforms of the terms, and so you get this.
Dr. Willis, quick
Yeah.
question. Should we expect something where a could equal an exponential, and so would b?
I don't think you'll see that on the exam.
Okay.
Yeah.
Okay, good. Thank you.
So if you have quadratic terms up here in the numerator, you can get more complex realizations of this. Remember, for the midterm exam, we only have 75 minutes. I'm not going to test you on doing super fancy partial fractions. We don't have time for that kind of stuff. I will try and test breadth of knowledge, and so super complicated, detailed stuff like that is depth of knowledge. This is more a breadth of knowledge exam. You will be able need to know how to execute on your techniques for solution. But in general, you won't have to be doing like super, like I won't have any repeated roots, partial fractions kind of stuff or anything like that. We just want to have, in this case, what I consider to be fundamentals of partial fraction expansion. Any other questions before I go on? Okay, difference equation to Fourier transform. Okay, so that's pretty straightforward. We did that a couple of times already. And so you have a difference equation. You take the Fourier transform. Everywhere you have y of n, you plug in y to the j omega. When you have a delay, you kind of have a delay term that you multiply. So this is an advance of 1, and that leads to this factor here. Then you factor out x. You divide through. You get h is equal to y e to the j omega over x e to the j omega. And that's this thing here. And by previous examples, if we wanted to get h of n, all we have to do is inverse transform that. What would it be? It would be
delta. It'll be
delta of n plus 1 minus delta of n. Of course, and that you could also get by just plugging a delta in for x here, right? So it's all this is the circle of DSP life, right? For LTI systems. Anyways. So let's see here. This is a FIR1. This is an IIR1. Well, let's go to the DTFT domain. We take the DTFT. We factor out y, and so this is y is in both terms here. We factor it out, and we get 3 minus 2 e to the minus j omega. That becomes the denominator, right? This term and this term minus 2 e to the minus j omega. That makes up the denominator terms. And then on the right side, well, the x's are 3 minus 2 e to the minus j omega. Oh, wait, this is still the right-hand side. So here's, far over here is the actual left-hand side. Sorry, I have to move the chat out of the way. And so on the left-hand side, we have 4 x e to the j omega plus x e to the j omega e to the minus 3 j omega. So this ends up being the numerator, this term plus this term. And that's what you see in the top here. And so we've done that a few times. It's usually not a difficult algebraic manipulation, but definitely something you need to know. What are the 2 key things you need to know? If you want to do this directly without looking at any tables, you need to have memorized the delay property to figure out what factors of e to the minus j omega comes with these delays, and that the linearity. So you can make sure these factors come out, and then just be able to do the algebraic manipulation. Those are the skills that are at hand here.
And to get a numeric value, would we be given like omega?
Right. If you get an eigenfunction problem, right, and you say something like then it would be something like, hey, I input some kind of a complex exponential. Maybe it's a sinusoid. Maybe I input sine of 2n plus 5. Well, what do you have to do? What do you have to do if you want to find the output? And then the question, eigenfunction question would say, what's the output, right? So what do you have to do? You plug in the frequency omega is equal to 2. And you plug in, you find y of n is equal to the magnitude of h e to the j omega evaluated at omega equals 2. So you plug 2 in here, and you're going to get 4 plus e to the minus 6 over 3 minus 2 e to the minus 2. Sorry, e to the minus 6j, e to the minus 2j. That's a complex number. So the magnitude of that complex number will be out in front. We'll multiply it, and the phase of that it will add here. Does that make sense?
Yes, sir. I believe it does.
Yeah, and if I were to ask for the value of this function at some point, you just plug it in, right? What is the value of this for DC input when omega is equal to 0? It's 4 plus. Well, when omega is equal to 0, it's 4 plus 1 over 3 minus 2, right? So the value of this for DC input is 5.
Yep.
Okay, just kind of trying to remove any uncertainty there. It's just plug in. You got to. This is just a complex number. Just think of it that way. And all we have to do, if you have a specific value of omega, you plug it in, you get a complex number out. Okay. We're going the other way. Let's see, Fourier transform the difference equation. So we're going this way. Okay, so we just invert the process that we did before. So we start off, here we have a FIR system, and we just take HE to the j omega. Well, that's equal to y e to the j omega over x e to the j omega is equal to e to the j omega minus 1. And then we multiply over by x e to the j omega, distribute it out, and now we end up with y e to the j omega is equal to this minus this, and then you inverse transform. That'll give you y of n is equal to x of n plus 1 minus x of n. So it just goes the other way. Frequency response back to difference equation. And literally, we just did this problem, right? So if you want to go back to x as y as a function of x, you write it as y e to the j omega, y e to the j omega over x e to the j omega. Then you multiply it out and expand everything in inverse transform, and you got back. It's basically exactly the algebraic inverse of what we did to get the impulse response. Like if you follow these three equations in this direction, it is exactly the opposite of these three equations. We're just going this way, right? So, but to be exhaustive, just clear about how the triangle works, I write it out anyways. Okay, so we're at 2. We're going to have a 5-minute stroll through memory lane. So this is the basics of a DSP system. You have 3 blocks here, this analog to digital converter, processor, and a digital to analog converter. You put in a continuous signal here. The analog to digital converter gives you x of n here. Then you do something to x of n. That's the system. So we usually, if it's linear time invariant, we write it as h of n. It gives you an output. The output, if you want a continuous output, well, it goes through a digital to analog converter. Like this is exactly what's happening to my voice right now. It goes through the air, it hits a microphone sends it to the computer samples it, goes to a processor, my CPU right now, processor compresses it, maybe it's an MP3, what have you, and then it sends it over the internet, it gets to your computer, processor grabs that, decompresses it, generates a y of n. Y of n goes through a digital and analog converter that drives a microphone, that drives a loudspeaker that generates the acoustic signal that you reach as your ears y of d. It's just a system. They're all over the place. They're very important and part of everyday life that we engineer. So we know all about this. So sample period, sample rate. So T is the sample period. Has units seconds per sample. Sample rate has units samples per second. And we talked about the sampling, how we go from a continuous signal to a discrete signal. The sampling process is periodic. We studied about periodicity and how to solve for periodicity. There's a very specific technique for solution. If you want to find if a sinusoid is periodic, first of all, not all discrete sinusoids are periodic. Only those that have a discrete frequency that is a rational number times pi are periodic. And if they are a rational number times pi, here's your technique for finding their fundamental period. Do other periods exist? Yes. Any multiple of the fundamental period is also a valid value for the period. So here's an example of a solution. So I'm actually going to, I don't know. So I think I'm going to stop right here. And I'm going to allow students and just open it up to students for 13 minutes, maybe a little bit more. Because I feel like if you're able to have solved what we're doing right now, this stuff you actually already know. So I kind of want to focus on things that you want to ask me that might not be totally clear. So having said that, go ahead and ask any question you might want to ask.
I do have one question when it comes to like convolution.
Yeah.
Like when I was doing on one question on both the homework and the quiz for that, I did like both the MATLAB conv function and the table function on paper.
Mm-hmm.
One thing I was having trouble with, I'd get the values right, but I'd get the points on the x-axis wrong. Like they'd be the right values, but be on the wrong spot. how do exactly we know when those spots shift?
All right, so the rules for doing so, if it's an FIR filter, then the start index and the end index will be actual values. And so on slide 37, we kind of talk about what happens for an FIR signal. So I'm assuming that we're going to talk about an FIR signal for now. If it's an IIR signal, you have to kind of figure out where the two. So if the output is IIR but starts at a specific place, you can use the start index rule that's written here, but there will be the end index ends up being infinity because either one or both of these values here for the end index is infinity or negative infinity, depending on how, if it's time reversed or not. But let's talk about these start indices. So the way that I suggest you look at start indices is you look at your signal. If it's two finite length signals, you need to find the first index that is non-zero for both signals. Okay? In this case, the first non-zero index is 0. Right? So this value -2 actually occurs at index 0, and this value 1 actually occurs at index 0 for both of the signals. That means that the first non-zero output, or the first output of this convolution problem, rather, I mean, you could actually have a 0 value if there were zeros in the signals or something, is going to be calculated at the sum of those two indexes, ns1 plus ns2. So the first output would actually be at n equals 0 for this. And the end index for the convolution will be at the sum of the end indices of the signal. So the last index of the output will be at index 7. So when we look at the output here, this index here is for n equal to 0. And then this index here is n equal to 7. And so that is my, for two FIR filters, as long as you can identify the first non-zero value of the two filters and the last non-zero value of the two filters, you have this straightforward equation. I used to prove it, again, one of the many things, I used to prove that this equation is true, but I no longer do this. I just state it and I say, use it. So
If we wanted proofs, we'd be math majors.
Yeah, I mean, fair enough. I mean, I think it's debatable, you know, but sometimes there are proofs like you learn something in the proof itself, like you learn some insight. So sometimes it can give you a little bit of engineering insight. But you know, I'm also sensitive to what you said, and there are times when maybe all the gory details isn't super useful, but anyways, I get where you're coming from. So does that help?
It helps tremendously, sir. Thank you.
Yeah, you bet. And that's so just keep that in mind. That's a really helpful way. But the one thing that can trip students up is if you misinterpret, like if you get a signal like this and it says something like for -1 is n is greater than -1 and less than 5, right? And then you just end up using these indices, right? Actually, this is also a correct way of stating the bounds, right?
Right.
And it's only like the first non-zero value is actually at 0. So if you get bounds like this on your n, make sure that you kind of say, okay, well, that means that the actual values of a signal are non-zero for 0 to 4, right? Don't just kind of like look at the equation. Take some time to interpret what's going on. Just don't you know, like always take a second and cross-validate, kind of cross-check what you're doing. Does that make sense?
Yes, sir. That's what I was doing more on that.
Okay, yeah.
Dr. Willis, quick question. Shouldn't the bounce of the summation be from k is equal to 0 to 7 for y of n?
Let's see. In this case, we plugged in h of k. We took this guy, right? And this guy only exists from 0 to 3. So, yeah, this guy sort of drives the boat here.
Okay.
Yeah, this one, h of n, is only non-zero from index 0 to 3. So, that's, and so...
But shouldn't we be running the indices from 0 to 7, though?
No, h of 4 has the value 0, so you can go to 7, but it'll be at index. So at index. So when I write down h of 4 times x of n minus 4, h of 4 will have the value 0, right? So that's why when you're doing these convolutions, if you decide to do it analytically, I always kind of suggest plugging in the sort of thing that has more complicated bounds here, because you don't have to deal with all the algebraic manipulation of this delay. And so the thing that often controls the convolution is whatever ends up being in this sort of fixed position.
The stationary function, right?
Yeah, the stationary function. Yeah, this does not shift with k. This does shift with k.
All right.
And so when I do it this way, since h is not shifting, it sort of controls whatever is put in this place controls however many rows that there are. And so there are 4 values, so that there end up being 4 rows. One for h of 0, one for h of 1, and one for h of 2, and one for h of 3. So 4 rows. Okay. Any other questions out there?
Oh, can you also talk about IIR, like for the endpoints? I was struggling on that.
IIR for convolution.
Yeah, for convolution.
Yeah, so don't forget the properties, by the way. So these properties are important. Let's see if we can find the IIR convolution stuff. Why is this thing fighting me? So we're at 39. Oh, here, sinusoids are here's eigenfunction problems. Just a review of the eigenfunction property. It doesn't look like I have IIR convolution here. That's okay. So if I were on the exam, I would say let's jump up to lecture 5, where we talk about that. And I would jump here because I know that this is sample domain representations for LTI systems. And then I would go and scroll after I could get this zoom out of the way. I grab the scroll bar and I'd zoom down to IIR convolution, which should be here. Okay. And so by the way, there's a number of also solutions to this available in the worked solutions. But the technique for solution is simplify the bounds is the first thing. You always want to simplify your bounds, and then once you've simplified your bounds, calculate where the product of the two step functions are. So if you have an IIR system, it'll usually be represented as something multiplied by a step function. So then you find the bounds of the two step functions, and then you find the bounds of the product, and the bounds of the product are going to tell you what your summations are going to go to. In this case, it goes from 0 to n minus 1, because those are the bounds. 0 is less, k is greater than or equal to 0 and less than or equal to n minus 1. And that's what sets up the bounds, and then everything else follows after that, because everything else is an algebraic manipulation after we get the bounds right. So that is the key to solving these IIR convolutions. So before, and I'm going to just jump one more time to the files, to the solutions, where you see, even if you have this time reversal, there's examples of stuff there about how to work that out. Here's some IIR. So here's some stuff for that shows you how to work with the IIR. So you can always go to the solutions and see other examples of worked IIR from the homework. Okay?
Oh, I see. Mainly I was trying to hit on like when we had to use a table, like for the example you had for FIR. So if one of them was like a unit step, it goes all the way to infinity. So how would we do the table there?
There is no table solution for infinite impulse response convolution. Yeah, if there were a table, if there were a simpler way to do this, after 17 years, I would know.
Okay.
This is how you solve that. So, I mean, wait a second. So, is there a simpler way? Well, sure, there's another way to do this. By the way, like, does anyone want to suggest? Like, we know the triangle of fate now.
Yeah, we do a Fourier transformation to it.
Yeah, you can do a Fourier transformation, right? What is the Fourier transformation of this? This is 1 over 1 minus 1/4 e to the minus j omega, right? This over here is 1 minus 1/3 e to the minus j omega, and it's got a delay, so it's e to the minus j omega. And so the convolution of the two is the multiple of these two. So this is, in fact, the output, y e to the j omega. If you can inverse transform this using partial fractions, you have the solution.
So,
Yeah,
so in the exam, are you going to ask us for a specific way to solve?
No, absolutely not. Why would I do that?
I don't know. Maybe you didn't have enough coffee.
No. Listen, if you like, I want to keep repeating myself. If you use the techniques of this course to solve the problem, like if you're using DSP theory in the correct ways to solve the problem, then you will get it correct. So this is using DSP theory. So like, hey, you know what? I'm going to do this. I've got my triangle of fate. I don't feel like doing all this manipulation in the sample domain. I'm gonna take my triangle. Dr. Willis, I know my triangle. That's fine. I'm going to take my triangle, and you told me that you want to get the convolution, right? And so you gave me two functions here. I'm just going to go this way. I'm going to go this way, and then I'm going to go this way, right? And I'm going to get my output that way, because we're trying for a y then, right? And so that's all fine. And so if you, or you can just go this way and back, right? You can, we're dipping it, we're going across that edge, right? So that's fine. Is that, so maybe that helps. Maybe that's another way, There,
Yeah,
so
the way that I used it was like I put them together in summation, but I evaluate one at a time. Like instead of multiplying the bonds, I just do one at a time, and it worked on the homework.
I would not do that. That doesn't. I don't understand how that could work the way that you described it, but I would.
Yeah, it worked on the homework, pretty much all the programs.
Okay. I hope it works for you on the exam, but it doesn't make any sense to me.
Okay.
So, anyways, any other questions? Well, it's after time. So if there's any other questions, you'll have to stay after class. I'll continue to record for a few minutes. But hold on a second. Let me. So some folks may have to leave. So I'd like to dismiss class for those folks that would like to leave. Now, if you'd like to stay, you're quite welcome to stay on and continue having the discussion about the midterm and kind of prepping. But if you'd like to leave, you're absolutely welcome to do that. I'll continue to record until we stop talking. So if you want to review anything discussed after you leave, it'll be in the uploaded video. All right. So thanks for all of that, and class is dismissed. But for those that wish to stay, continue.
Right. So, slide 9. I just wanted to see what your favorite way of factoring it is, whether it be like quadratic formula, or do you just pull out the numerator to make it 1? It's obviously easy factoring, but I'm just wondering what you would do.
What's going on slide 9? Not on this lecture. It was slide 9 here.
Slide 9 lecture, yeah.
Okay, slide 9 here. Okay, so what's my favorite way to factor?
Yeah, the negative 1 over a s squared.
So you mean like how would I go about factoring this?
Yeah, I mean,
I always suggest just using the quadratic formula.
Yeah.
And okay. So minus b plus or minus the square root of b squared minus 4ac over 2a, and this is tried and true, and never, you can't go wrong. Albeit you might have to do, since we have fractions here. You might have to do some manipulations, but because you get 2 over 8, right? But that's what I always recommend.
Okay.
And having said that, I'll recommend one other thing, because I know that you're all emerging MATLAB fans. So I'm going to show you that you can factor a quadratic in MATLAB with one command. Right, and so I'm going to just show you how one might do that. Roots. So I'm going to do help roots. So I kind of had MATLAB hoping that I could give you a little bit of MATLAB hints. This is a MATLAB hint. So roots will give you the roots of a polynomial. You would just type in its coefficients. So the quadratic comes first, then the linear, and then the constant. So roots, and then I'm going to plug in my a vector of constants. It's -1/8, I think was the first one. But then you have to kind of go from decimals back to fractions. What's the other one? -1.
Yeah, no, I totally forgot that
Minus
S squared. Yeah, we just use roots.
Yeah, -1/4 and 1. Okay, -1/4, -1/4, and 1. And then I press enter, and well, I hope that's right. -4 and 2. Okay, so therefore, so it says -4 and 2. But this, and again, this is where people get tripped up all the time. That is the factorization of this. But remember, we are, because of the way that we're factoring this, it's 1 minus that, so it actually ends up being the flip. It's basically you get the inverse of the actual root. So this is -4 and 2.
Yeah.
And I can explain to you why that is. It's because of the way that the terms are collected. Like, you can think of this as an S, right? So this would be 1 minus 1/2 S, but that's equivalent to 2 minus S, right?
Yeah.
You see what I mean? And so that's why MATLAB is right? Do you see what I'm saying? Because we're collecting the number with the variable, like when we inverse transform it. That's why it shows up as sort of an inverse thing.
Okay. Yeah. I'll definitely take more look into it.
I always worry a little bit by showing people that because of this. You have to remember this inverse thing. But I also, if you're in a bind, or you either learn how to do it with MATLAB and know how to use it, or factor it using the quadratic formula. They both give you the same thing, but if you use MATLAB, of course, don't let MATLAB use you. Use MATLAB.
Yeah, and so you're saying quadratic formula will definitely get all the right S minus 1/2.
Yeah, exactly. You'll get exactly the right roots. Here, you can put it in MATLAB, but then if you put it in MATLAB, you still have to go and put it in this form, because MATLAB will give you a factorization of this polynomial, and it'll be in this. So you would interpret this this result from MATLAB, see -4 and 2. To interpret that correctly in MATLAB, you're saying that it's a e to the j omega -4 or +4 times e to the j omega minus j omega. What's the other root? 2? Oh, sorry. What is it? So it's -2. Okay.
Thank you so much, Dr. Moss.
Yeah. Okay. So it looks like that, and because we collect the terms like that, it kind of looks weird. Anyways, is there any other question?
On the test, are we gonna be able to upload our work?
Yes, you're expected to upload your work for partial credit. If you do not upload your work for partial credit, you won't get any partial credit.
Is there a way to upload more than one file, for our MATLAB code and our work from there?
No, you just take pictures of whatever it is you want to upload. So if you're writing MATLAB, you just take a picture of your screen that has MATLAB on it.
Okay.
And so, important, if you do not upload this PDF, you cannot receive partial credit. So it's just one PDF, lump it all together, and send it in.
So, Dr. Willis, so there's no quiz today then?
I guess not. There was no time. There was. I intended that.
great.
I was intending for there to be a quiz, but looks like that didn't end
No
up
timeline.
happening. Yeah.
Well, thank you so much for showing some mercy then.
Oh, well, yeah. Anyways, it wasn't intended, I guess. But yeah, I'll take it.
Well, we're very thankful for you forgetting then.
So yeah. So anyways, I'm gonna wrap it up. If there's no other questions, of course, I'll be transitioning to virtual office hours for those that wish to go to the office hours. So at this point, I'm gonna stop all of these recordings that are in progress. Stop recording. Okay.
Recording stopped.
Hope you get well soon, Dr. Willis.
Thank you. That's very kind of you to say. So do I. I do expect to be in person, of course, with proctoring the exam on Tuesday, and which implies able to move. All right.
Yeah.
So.